Okay, good morning everyone. Thank you for the introduction. So today I'll be talking a little bit about WPA3 and Wi-Fi security. So maybe to set the stage, when I'm talking here about exploits against WPA3, I'm not immediately talking about recovering the Wi-Fi password. We have been getting better at security, so that fortunately has been getting harder to just recover the password. But there is still a lot of fun things we can do with WPA3. We can mess with the bandwidth of other users, we can still disconnect users, we can still crash devices. And in some cases, we can still have some previous attacks where getting the password is easier. Now, before we get to that, let me quickly introduce myself. Well, there already wasn't a good introduction, so I'm a professor at KU Leuven University, and I really do research over the full network stack. So a lot of my past work have been about Wi-Fi security, but I do network security in general, and I try to bridge the gap between theory and practice. And yeah, today I'll be talking a little bit about Wi-Fi security and WPA3. And I first want to give some history about Wi-Fi security and what all happened in the past. So if you look at the beginning of Wi-Fi security in the early 2000s, we had WPA1 and 2, and at the time these were really the best kind of protocols we could have for Wi-Fi. But if we look back, the security in WPA2 is really quite lacking. And why is that the case? Well, first and for all, it's because WPA2 is vulnerable to offline dictionary attacks, meaning an attacker can capture a handshake that a client uses to connect it to a WPA2 network. That attacker can take the frames that are exchanged during the handshake and then use that information to try to brute force the password offline without even being near the Wi-Fi network. And this is a well-known attack. Now, WPA2 also has some weaknesses that are maybe less mentioned in the past. And one of them is that WPA2 does not offer forward secrecy. Meaning you can capture the traffic of a WPA2 network today without knowing the password, but if in a year or two you learn the password, you can go back in time and decrypt data that you captured before. And the third problem, which we'll also focus on in this talk, is that in WPA2, only data frames are protected. And you also have management frames that, as the name implies, they manage the connection between the client and the access point. Those are actually not protected at all. And there's one famous attack that results from this called the deauthentication attack. So who here has heard about the deauthentication attack before against Wi-Fi? So I see some hands. And basically it's a very simple attack. You as an attacker can spoof plain text deauthentication frames to forcibly disconnect a client from a network. And this is because WPA2 does not protect management frames. And yeah, we were using WPA2 for quite a long time. And for quite a long time, there were also no real advancements in Wi-Fi security. And that started to change around 2016, 2017. At that point, we discovered the key reinstallation attack, so the Krack attack against WPA2. And yeah, it allowed you to decrypt some frames, to replay some frames as well. But perhaps more important than what an attacker can do with this attack is the influence that it had on, I would say, the Wi-Fi community, so the IEEE and the Wi-Fi Alliance. Because after this discovery, I feel that they finally took security a bit more serious. Because yeah, this Krack attack also was a flaw in the standard, so they started now to also define and release new security protocols. And that is how we got WPA3 in the year after the release of the Krack attack. The Wi-Fi Alliance finally made WPA3 public. And to give a quick background about what WPA3 is, WPA3 introduces two main additions on top of WPA2, I would say. The first is that with WPA3, your device will use a new handshake to connect and authenticate with the network. And this handshake is called the Simultaneous Authentication of Equals handshake. That's the technical term. In practice, it's often called the Dragonfly handshake. And this handshake provides the usual properties. So you have mutual authentication, meaning you authenticate the network and the network authenticates the client. And this handshake negotiates a new session key that will be used to encrypt data frames. The most important thing here is that WPA3 will also offer forward secrecy, and it prevents these offline dictionary attacks. And in practice, that basically means that you can use a relatively short password while still being secure. Because if you use a short password with WPA2, then you could brute force that offline, but with WPA3, that becomes harder. Because with WPA3, the idea is that the only way to verify if a password is correct is to really try to connect with that password to the network. The second important addition of WPA3 is that it requires the use of what is called management frame protection. And that basically means that these management frames, so think these deauthentication frames that can be used to disconnect the client, they are now authenticated, meaning an adversary cannot spoof them. So the idea behind management frame protection is on one hand to prevent these denial of service attacks, and some other management frames are also authenticated when you use management frame protection. So that's a quick history behind WPA3. To give a comparison with some other attacks in the past, so in 2019 we discovered the Dragonblood attack against WPA3. To give a high-level explanation of what this attack did, basically we discovered that the time it takes for an access point or a client to reply to a handshake message, that leaks some information about the password. So basically, we as an attacker can try to initiate an incomplete handshake with a network, even when we don't know the password, and we can see how long it takes for the access point to respond, and that leaks some information about the password, meaning we can still, with that information, with that timing information, do offline brute force attacks against a WPA3 password. And you may be thinking, oh, timing attacks, that might be hard in practice. But we discovered that these attacks are quite feasible because often an access point isn't the most high-performant device, especially a home router, and there these timing differences were really noticeable in practice. Another recent addition on top of WPA3, and this is the last piece of history of Wi-Fi security that I want to introduce, is that WPA3 not only has this protocol to protect your home network, there is now also an extension of WPA3, which is called SAE public key, and this is used to protect hotspot networks. So, imagine the case where you have a conference like here, or you have, say, a coffee shop where you have a Wi-Fi network, then often what people do is they give the password of the network to all the attendees and to everyone that visits. Now, if you use WPA2, there is actually little advantage towards using encryption and then giving the password to everyone. Because if I, as an attacker, know the password of the network, I can simply set up a copy of the network, and then the protection you use doesn't really matter anyway. So with WPA2, using a password to protect a hotspot network, like a conference network, is actually quite meaningless. But with this SAE PK protocol, you can actually protect a hotspot using a password, while an attacker, even if the attacker knows the password, will not be able to set up a clone of that network. And I will explain later in the talk how this is done, but basically, this new protocol relies on public key encryption. Okay, so that's a quick history about Wi-Fi security. Let's now get into the more meat of the talk, namely attacking some parts of WPA3. And in this talk, I'm going to focus on two aspects. The first one is to attack this management frame protection, to still perform denial of service attacks against a WPA3 network, and also some other vulnerabilities. On a few of these attacks are not yet patched, so I guess you can still consider them 0 days, because no patches available for some of them. And I'll also be talking about some tool that we made to actually perform these attacks. Okay, so let's get started with management frame protection. And let me first make sure that we're on the same page here. So, to repeat part of the introduction, in Wi-Fi there are 3 types of frames. So you have your data frames here that are encrypted when you use WPA2. But apart from that, you also have management frames like deauthentication frames, and you have control frames to acknowledge messages more at the, I would say, the physical layer. And WPA2 only protected data frames because management frame protection was not required. But with WPA3, these management frames now do have to be protected. And what does that mean, that the management frames have to be protected? Well, that means that deauthentication and disassociation frames have to be protected. And the idea is that that prevents these trivial denial of service attacks where you can disconnect a client. And there's also some other types of action frames, which are management frames that are protected, but these are less important for our talk. Now, one very interesting observation is that management frame protection has existed now for more than 12, 13 years by now, but only now is it becoming required. So that is actually really surprising, because this has existed for more than a decade, but people never used it in practice. And why was that the case? Well, I think the main reason was, it's not required. So as a vendor, you won't immediately implement it because, it's not required. And the implementations that did exist were often buggy and might result in your clients not being able to connect. But now with WPA3, management frames is required, and that's why we looked at the security of management frame protection. And we analyzed the standard. So we did a manual analysis of the standard to see whether all the cases are covered. And then we also did, in a sense, an audit of some implementations to see if we can still find denial of service attacks. And let's first give a summary of the findings we found when analyzing the standard. The first surprising thing that we found is that some management frames are still not protected, even when you use management frame protection. So, 2, I would say, more exotic cases are that you have some ATEM frames which are used for power management in ad hoc networks, and you have some timing advertisement frames that are used in vehicular networks. These are management frames, but for some reason they are not protected. So as an adversary, you can still spoof with them, so you can probably still drain the batteries of a device in an ad hoc network to attack devices. A third important management frame that is not protected when you use WPA3 are beacons. On beacons, they basically announce the presence of a network, so they are sent periodically, so you have 10 beacons generally per second, and all Wi-Fi networks will use beacons to announce the presence of a network. So even if you have a hidden Wi-Fi network, that hidden Wi-Fi network will still continuously be sending beacon frames. It's just that those beacon frames don't contain the actual human-readable name of the network, but even a hidden Wi-Fi network uses beacon frames. And there is an optional defense that protects these beacon frames, but it's not required as part of WPA3. So in practice, these beacon frames are not protected and you can mess with them. So then the question becomes, okay, even with WPA3, we have plain text, unprotected beacon frames. What can we do with that as an attacker? And there are actually quite some fun things that we can do by spoofing beacon frames. The first is that beacon frames, they advertise the maximum transmission power in a Wi-Fi network. And we can then spoof a beacon frame that will lower the maximum transmission power of a client, and that may then cause the client to disconnect from the network because the client will use such a low transmission power that the access point won't receive its frames anymore. And there's even a custom extension by Cisco to beacons that again allows an attacker to lower the maximum transmission power of a client. In fact, we found an interesting implementation in this. So Linux has basic support for this Cisco extension in the kernel. And there we found that if we use a negative value for the maximum transmission power, then Linux, the kernel, doesn't know what to do and it will simply disconnect from the network. So if you want to disconnect a Linux client from a WPA3 network, you can simply spoof a plaintext beacon and put a negative transmission power. Now let's actually see a quick demo of this. So here we have a client. It can still visit a website normally. Now as an attacker, we're going to spoof some beacon frames. In this case, we inject 10 beacon frames to make sure at least one is received by the client. And if we now look in the debug output of the victim, we can indeed see that the beacon frame was received and it limited its transmission power. If we look at this malicious beacon in Wireshark, we can also see there's an element here which specifies a power constraint. And if the victim now tries to reload the page, you can see that the page can't be loaded. If we try to visit another page, this page also isn't loading. And the reason why is because this victim is now using such a low transmission power that its frames just no longer reach the access point. So this is a fun little denial of service attack. The interesting part of this attack is that beacons are also broadcast frames, meaning by spoofing a single beacon, you're essentially attacking all connected clients at once. So in that sense, it's also quite an efficient attack. So that's the first attack that's possible by spoofing beacons. A second attack that's possible is that we can force a client to wait a longer time before they will transmit frames. So if you're a bit familiar with how a wireless network works, usually when a device wants to send some data over the wireless medium, the device will first check, okay, is someone else transmitting? And if someone else is transmitting, it will wait a random amount of time before trying to transmit again. On the time that a client waits, this amount of time is specified in the beacon as well. So what we as an attacker can do, we can spoof a beacon that basically says, okay, if you want to try to transmit a frame, first wait a long time before you transmit it. That's the summary. And this basically means that we can lower the bandwidth of a victim because we can cause this victim to always wait a long time before the victim will send the next Wi-Fi frame. And here we again have a demo of this. So in this case, I think it was either an Android or an iPhone. And we can see without an attack present, we have around 10 megabit speed. We now again inject some beacons. We set these malicious parameters that cause the client to wait a long time before sending the next frame. So these are called the backoff parameters. And if the client now does a new speed test, we can see that the bandwidth indeed has significantly decreased. So you can imagine if you're at a hotel or some network and you notice that your internet is slow, you can perform this attack to lower the bandwidth of other people, and then you will have faster internet. There are also some other attacks possible by spoofing beacons. These are a bit more technical attacks, so you can establish a special machine in the middle position, which is then useful to perform more advanced attacks like a key reinstallation attack, and so on. By spoofing beacons, you can also trick a client into staying awake longer than it normally would. So say against an IoT client, you can abuse this to make the client stay awake for a long time so you can deplete the battery. and so on. And what's the defense against this? Well, one possible defense is to use this beacon protection defense. And when you use beacon protection, which is an optional feature of WPA3, then beacon frames will get authenticated, meaning an adversary will not be able to spoof these beacon frames anymore. And yeah, beacon protection is actually a defense that we created and published ourselves. It has meanwhile been standardized by the IEEE and is now an optional feature of WPA3. So that covers some of the attacks that are possible by spoofing beacons. We also analyzed some other aspects of the standard. And yeah, I'm not going to bore you too much with the details of the standard, but I do want to give you a high-level overview so you have a bit of feeling with it. And there are basically 10 main rules that specify how a client and access point should behave. And these rules are quite complex because a lot of these rules are conditional on some parameters. For example, whether a rule applies depends on whether the client supports it, whether the access point supports it, whether the key is already negotiated, and so on. And yeah, here you don't need to read this, but this is how these rules look like. So you can see they're not that trivial to parse. And the words here that are highlighted in bold, those are some of the conditions that must be true. And if those conditions are true, then this rule applies. So if you have to implement this as a programmer, you have to carefully read all these conditions, check for them, and only if these conditions are true, implement the behavior. So it's not that easy to implement this correctly. In fact, we found that in the standard there are even some rules that contradict each other. So for example, there are 2 rules that specify how you should handle unprotected deauthentication frames while you are still connecting to a network. And some say, okay, just drop these, but other parts of the standard say, oh, you have to start this special SAE query to see whether the client is still alive. But basically this just shows that the standard is quite complex, meaning it's also hard to implement correctly as a programmer. And some special edge cases are also undefined. So there are some scenarios where the standard doesn't say explicitly how a device should behave, meaning, yeah, then it's up to the programmer how to implement this. And these programmers are not always security experts, so sometimes that can go wrong. So basically, in my opinion, the standard can be more clear. Currently, the standard is unclear, and that might lead to some implementation issues. And there's, in fact, one rule in the standard which is very clearly insecure. Basically, there is one rule that says, okay, the receiver shall process unprotected frames. That's, of course, not what you want. Now, this does occur in the edge case. So basically, the standard is saying while you are still connecting to a network, meaning you don't yet have keys to authenticate these frames, then it's also hard to, you cannot authenticate the frame. So what are you going to do? And in this case, the standard says, okay, just accept them. And as an attacker, of course, you can abuse this because when a client is connecting to the network, you can spoof these plain text, these unauthenticated deauthentication or disassociation frames to cause the handshake, to cause the connection process to fail. Now, this is a bit unfortunate because it's actually quite easy to defend against this attack. Namely, what you can do is when you receive one of these plain text frames, instead of immediately accepting it, you can just start a timer instead of disconnecting. And if before this timer expires, the connection process progresses, meaning the next phase of the handshake has been successfully executed, then you basically know, oh, actually this client is still connected because it's still standing frames, meaning this deauthentication frame probably was from an attacker. While on the other hand, if you notice that there is indeed no progress, if the client indeed isn't sending frames after 1 or 2 seconds, then you can indeed disconnect the client. So that would be a much better solution. Now, how can we fix these issues here? So we have some of these edge cases that are badly handled in the standard. Well, a long-term fix is to simply always require management frame protection. So even with WPA2, because that would simplify the rules in the standard. Of course, in practice, you can't really do this. In practice, you need backwards compatibility. So in a sense, this is a dream for maybe in 10 years. What can we do in the meantime? In the meantime, we can update the standards to make these rules more clear. And that's exactly what we did. We presented some updates to these standards and presented them at IEEE meetings, and hopefully they will be adopted. Okay, so that covers some analysis of the standards. And I want to get back to looking at implementations to really audit some code to see how management frame protection is implemented in practice. And our goal here is to look for attacks that still allow you to disconnect the client from a WPA3 network. Because currently our assumption is that with a WPA3 network, it uses management frame protection, therefore these deauthentication attacks are no longer possible. But my message here will be that actually these disconnection attacks are still feasible by abusing implementation flaws. And concretely what we did is we inspected some open source implementations, and we looked for functions in a Wi-Fi client or in a client that cause a client to disconnect from the network, and we then looked whether we can trigger these disconnection functions, basically. And maybe to briefly go back to the previous slide, why are these denial of service attacks actually very useful in practice? Well, the first one is, okay, an attacker might be purely interested in disconnecting the client from the network, so that's one obvious use case. But another important advantage of these disconnection attacks is that they are often the first step in more advanced attacks. So if you look at previous attacks in Wi-Fi, like the Krack attack, the Frag attack, and the Dragonblood attack, they all target the handshake that is being executed when you connect to the network. Of course, once a client is already connected to the network, that means you cannot perform these attacks because there's no handshake going on. But if we have these disconnection attacks, then even if a client is already connected, we can use these denial of service attacks to disconnect the client from the network. Then the client will immediately reconnect, and then we can try to perform these more advanced attacks. So these attacks that we see, they have as purpose, of course, a denial of service attacks, but they also are a first step in more advanced attacks, typically. And what we did is we looked at some implementations, and we saw whether we can trigger some of these disconnections by spoofing plain text frames. And we first looked at open source implementations, and then we checked whether our attacks also worked against closed source devices. And we indeed found some fun stuff there again. So we again have our previous case where we can spoof beacon frames, because beacon frames are plain text, they are unauthenticated, meaning they are easy to spoof. And basically we found some new implementation vulnerabilities in how beacon frames are handled. To give a high-level explanation here, a beacon frame also contains the current channel and bandwidth that a Wi-Fi network supports. For example, a beacon can say, hey, I'm a Wi-Fi network on channel 60, and I have a 40 megahertz bandwidth, and it can give all those details. What we as an attacker can do, we can actually spoof a beacon with an invalid channel and bandwidth combination. And to give a summary of this, not all bandwidth sizes are allowed in every country, basically. Meaning, here is one specific example. if you spoof a beacon that says, okay, I'm a Wi-Fi network on channel 1, and my secondary channel is below the primary. This is just a technical way to specify on which frequency the network operates. This specific case is invalid in a lot of countries and a lot of regulatory environments, meaning most clients, when they receive this information, they will think, oh, the Wi-Fi network is suddenly using a different channel on bandwidth. I am not allowed to use that bandwidth, meaning I will disconnect. And we tested this attack against Linux and Windows. So we, as an attacker, spoof a beacon with this invalid channel and bandwidth combination. And then Linux and Windows will disconnect even if they are using WPA3. We also discovered a second implementation vulnerabilities on how some clients handle beacon frames. And this is actually a very general attack. Namely, a beacon frame, it can also contain a special channel switch announcement. And when is this used normally in practice? Well, when a Wi-Fi network is operating in the 5 gigahertz bandwidth, then clients on access points are required to support what is called radar detection. And the reason why is that a Wi-Fi network on a 5 gigahertz channel might interfere with a weather radar. And the idea is that if an access point detects a nearby weather radar on its channel, the access point will switch to a different channel to avoid interference with the weather radar. And when an access point then detects a nearby weather radar, so when it detects these radar pulses, the access point will also tell clients, okay, I detected a weather radar, I'm now going to switch to a different channel. And this channel switch announcement is included in plain text in these beacons. And here you see again a screenshot from Wireshark. So here you are basically saying, okay, my new channel is going to be channel 11, and I'm going to switch to that very soon, in one time unit. So, and in practice, we can abuse this to spoof beacons, to trick clients into switching to a different channel. And the clients will switch to this different channel, but the real access point is not on this channel, of course. Meaning the client will see, hey, the access point is now gone, it's not on this new channel, and eventually the client will again disconnect. And this is a very general attack. A lot of devices are vulnerable to this. So we tested this against Linux, against macOS, also iPadOS, iOS, and Windows. And all of these devices support the channel switch announcement, meaning all of them will switch to this channel that we tell it to, and eventually these clients will then disconnect from the network. So those are some of the attacks we discovered that are possible using beacons. We also discovered another interesting attack. Namely, we found this fairly recent router, which also supports WPA3. We found that if we flood this router with a lot of handshake messages, so here we have the SAE handshake, so the Dragonfly handshake of WPA3. If we flood it with a lot of handshake messages, eventually this router will just crash and reboot. And the reason why is that internally there is an out-of-memory issue, which leads to, in a sense, a memory allocation will fail, and then you get a null pointer dereference. And the interesting thing is this really happens in the driver of the router. So I also expect that other routers that use the same driver will also be vulnerable to this attack. And what is actually a bit funny about this case is that this vulnerability here is present in what is called the anti-clogging feature of WPA3. Now, what does that mean here? So WPA3 actually has a built-in defense to prevent against flooding attacks, because basically the WPA3 handshake is computationally quite expensive. And with WPA3, they added this anti-clogging defense, where if an attacker tries to flood a lot of messages, there's basically a basic defense to prevent an attacker from flooding the access point. The thing is that this anti-clogging defense is actually very trivial to bypass. So in the Dragonblood attacks, we showed that this anti-clogging defense is actually quite useless in practice. So in my opinion, there is really very little reason to implement this. But it turns out that, here, this vendor implemented this defense incorrectly, which actually led to a more severe denial of service vulnerability. So by implementing this defense, which is, in my opinion, useless, they actually caused themselves to be vulnerable to a much more serious vulnerability. So I think this is also a good general lesson here. If we think that a certain defense is useless, then it's best just to not implement it, because you might be increasing the attack surface. Okay. We also discovered some other attacks. I will just highlight them very briefly. Against Linux, we can also, even after a client is connected, spoof plaintext handshake messages. And by spoofing specially crafted handshake messages, we can also cause Linux clients to again disconnect, even when they're using WPA3. And there are also some attacks possible that allow you to replay management frames. But that is quite a specific attack. If you're interested to this, then you can read more about our research online. What I instead want to focus on now is how we implemented these attacks and how we tested for them. So, basically in our research, we are doing a lot of Wi-Fi experiments, and we want to make it easier to perform Wi-Fi experiments. And to do this, me, together with some colleagues from Northeastern University, we created a Wi-Fi testing framework to more easily perform some Wi-Fi experiments. And this testing framework is built on top of the Linux client, so the Linux host AP client. And we created a framework on top of that so that we can easily implement tests using Python. And what is the advantage of building a testing framework on top of Linux and on top of the open source Linux client? Well, the advantage is that this allows us to reuse some functionality of Linux. So for example, when we are now implementing some Wi-Fi test cases, we can reuse functionality of Linux to scan, for example, for the network that we are trying to target. And when we are targeting a client, we can very easily set up, in a sense, our own access point, which will transmit beacons. So normally you would have to manually implement code to scan for a network or to periodically broadcast beacons. But the Linux already has that code, so why not reuse it? Some other advantages is that a lot of Wi-Fi tools, when they inject a Wi-Fi frame, this frame will not be retransmitted if it is not acknowledged by the receiver. But by using our framework, if you send a frame to a victim, and if this victim then doesn't send an acknowledgement in response, by using the framework, it will actually automatically retransmit that frame, so your attacks are more reliable. Another important aspect is that these days we all use a lot of smartphones and mobile devices, and these devices often go into sleep mode, and that is often also an obstacle when testing a device, because when you are injecting a Wi-Fi frame, it might actually be that the moment you send it, your smartphone is asleep. So you might then be thinking, okay, my phone isn't crashing or whatever, the attack doesn't work, but actually you just sent a frame at the wrong time and your smartphone was asleep. With our framework, and basically again because we reuse the functionality of Linux, our injected frames will be queued until the device actually wakes up. So you have a bigger guarantee that the frames will actually be received when you are testing a device. And let me give you a quick feeling of how these tests are implemented. So, yeah, obviously you don't need to be able to read this, but I just want to highlight how you use this framework. And the idea is that you first define some triggers when a certain action should happen. So, for example, with our framework, you can say when you are connected to a network, then you inject a Wi-Fi frame. And you can further tweak these triggers on these actions, and you can also write some custom functions that can be executed. But basically, the idea behind our framework is that you have some triggers available, and in response to these triggers, you can program a certain action that should happen. And our framework also has a library with some common Wi-Fi functionality, like decrypting frames. We reuse the SAE library of Python, in case you are familiar with that. Another thing that I want to highlight is that to perform basic Wi-Fi experiments, and also to use our framework, you don't actually need a physical Wi-Fi network card. So that might be useful if you're ever trying to experiment with Wi-Fi. Linux has this special driver called Mac 802.11 hardware simulator, where basically you can simulate a Wi-Fi network card, meaning that you can perform experiments on Linux in a virtual machine without actually needing equipment. And that's, in my opinion, very useful to start playing around with Wi-Fi security on Wi-Fi in general. That's less important. Okay. The last thing that I want to mention here about this framework is that originally we implemented this framework really as a testing and auditing framework to test your own devices, which basically means that to execute these test cases, you need the password of the network. For example, if there's a trigger that says, once you have successfully connected to the network, then inject some frame, well, you can only successfully connect to the network if you have the password. So our original goal of this network was really to act as a testing framework. However, you can fairly easily convert this to what I would call an exploit framework by using triggers that are possible even when you don't know the password of the network. So instead of saying, once you connected to a network, inject a malicious frame, you can instead say, okay, once you detected a network, then inject the frame. So in a sense, this testing framework can be easily turned into an exploitation framework. And yeah, we have the link to the framework here at the bottom. In the conclusion slide, we'll have this link again, in case you want to take a picture of it. But basically, we now added some support to also not just test devices, but to also attack networks. Okay, so now in the last part of the talk, so we now covered management frame protection and what you can all do with that. In this last part of the talk, I want to focus a bit on this new hotspot protocol to secure Wi-Fi hotspots. And this is a sense, you could say it's an optional part of WPA3 in a way. So what is the goal of this new protocol, this new SAE PK protocol? The idea is that we want to authenticate a hotspot using only a password, but prevent an adversary from using this password to clone the network. Because with WPA2, if I know the password of the network, I can simply plug in my own router, fill in the same network name and password, and then people would connect to it. But we want to prevent this. We still want to be able to hand out a password to users, but only with this password, an attacker shouldn't be able to set up a clone of the network. And how is this accomplished? Well, to give a high-level overview, the network, so the access point, will generate their own public and private key pair. And then the Wi-Fi password will be derived from this public key. So the idea is that as a user, you no longer get to pick your own password of the network, so you can no longer pick a list of words or some random characters. That's no longer the case. The password will now be automatically generated. And the idea is that when a client now connects to the access point will send its public key to the client, and the client will then be able to use this generated password to verify the authenticity of this public key that it received. So basically, this Wi-Fi password, in a sense, acts as a signature of the public key that the client can use to verify the authenticity of the public key that it receives. So basically, this is what is mentioned here. When a client connects to the network will send the public key to the client. The client uses this automatically generated password to verify the authenticity of the public key. And then the access point will prove that it possesses the private key that corresponds to that public key. So the takeaway message here is that the password forms a signature of the public key. So that's the one thing I want you to remember. If you ever see this SAE PK protocol again, here the Wi-Fi password acts as a signature to establish trust in a public key. Now, how is this accomplished in practice? So how is this password generated? Well, this password is generated by taking the hash of the SSID, so the name of the Wi-Fi network, and also of the public key, of course, which in this case is a point on the elliptic curve, but okay, that's less important for us. And then we also have this this second parameter here in the middle. What do we mean with the modifier m here? Well, this is actually fairly simple. It's simply a number that starts from a random value and is then incremented by 1 until the output of the hash function starts with a certain amount of 0 bytes. So that's what is mentioned here. Basically, this can be a security parameter of the network because this modifier m, okay, it's a random number, it's incremented until 1, until the hash output starts with either 3 or 5 0 bytes. And whether you pick 3 or 5 0 bytes, that's in a sense decides the security of the password. So if you require here that the output must start with 5 0 bytes, then you will end up with a more secure password, basically. Now, let me make this a bit more concrete. So let's say that we actually generate a password in this way. Then an example password will look like the following sequence of letters here. So the output of this hash function, the first leading 0 bytes, they are removed. Then you take some bits, some remaining bits, and you convert them into a human-readable form. And the length of the password here is decided by the network as administrator. So if you want, you can also use a longer password to make the protocol even more secure, if you want to. And yeah, in the weakest possible configuration, this password has to encode at least 52 bits of output of the hash function. Now, let me try to give a bit of intuition on why it's now much harder to attack this protocol. Let's say that we as an attacker now know the password of the Wi-Fi network. So we as an attacker are given this password. Then the question is, can we now set up a rogue copy of that network where clients will successfully connect to? So the question is, if we have this password, what do we have to do in order to set up a rogue clone of this network? Well, what we as an attacker have to do is, we have to find our own public and private key on our own modifier value, so our own counter value, that will result in the same hash output. So the question here is that if we want to do a naive attack, we basically have to find our own public and private key that will result in the same password as the real network. So basically we have to, as an attacker, we can generate our own public key and then try a lot of modifier values, so a lot of counter values until we have the same hash output. And what's the complexity of this? So how long does that attack take? Well, in the weakest possible security setting, the hash output has to start with 3 0 bytes, meaning we have a complexity of 2 to the power 24, and then the remaining bits must also equal this password, and the minimum password length encodes at least 52 bits of this hash output. So basically, if you want to perform a very naive attack, you have to perform almost 2 to the power 80 operations, and this is pretty much infeasible for an ordinary user. And this is why it's not possible to perform this attack in practice. So I hope that that is a bit clear. There is a bit of a more theoretical attack against this, because as an attacker, what we are in a sense doing is we are inverting this hash function. And to invert a hash function, you could also use rainbow tables. So there is a bit more theoretical attack where you can construct a rainbow table for a specific network name. And once you construct this rainbow table, you can then use it to attack any network with a given name. So for example, you can construct a rainbow table for the network name Starbucks, and then you can use that table to more efficiently attack all networks that are called Starbucks. So basically the name of the network acts as a seed to make these rainbow table attacks more time consuming. Now these attacks are still very theoretical. For example, a rainbow table would be about 60 terabytes large. And even with such a large table, breaking a password, I mean, we estimate this, it would still take 2 weeks on an Amazon instance that has powerful GPUs. So, this attack exists in theory. In practice, it's maybe on the verge of practicality, but it's definitely not a trivial attack. And you can prevent this by using long passwords, or by using the security parameter where you make the hash output start with 5 0 bytes. So this is a more theoretical attack. What is, however, a much easier attack against these hotspot networks is to use very simple network-based attacks. Because, the goal of SAE PK is to prevent an adversary from cloning the access point. And the reason why we want to prevent this is because the adversary can otherwise intercept our traffic, right? I mean, that's what we want to prevent. But there are also other attacks that we can perform to intercept the traffic of a victim in a Wi-Fi network. And what attack is that? Well, we can just perform attacks at the network layer. Because this is a hotspot network, meaning we as an attacker can connect to the hotspot and then use typical network-based attacks such as ARP poisoning to redirect the traffic of a victim towards ourselves. And the reason why is because the SAE PK standard doesn't prohibit client-to-client traffic. So if you implement this protocol according to the standard, then clients are still able to communicate with each other directly, meaning attacks like ARP poisoning is still possible. So I assume ARP poisoning is well known, but to give a very quick background about it, basically we as an attacker can connect to the same network, and we can basically tell the client, hey, I'm the default gateway now, send all the traffic towards the internet to me. Then the adversary will forward this to the real gateway, so to the router. And we can do the same to the gateway. We can tell the gateway, hey, I actually have the IP address of the client, meaning the gateway will send the victim's traffic to the attacker, and then the attacker can forward it to the client. So, this is a very straightforward attack. If you don't know about this, I recommend that you read it online because it's also very easy to perform this attack. A second vulnerability that is still possible in these hotspot networks, and this is the last thing I want to cover, so we still have time for some questions, is that in a Wi-Fi network, we also have broadcast traffic. So broadcast and multicast packets. And the way that these are protected in a Wi-Fi network is that there is basically one symmetric key that all clients possess, and that key will be used to decrypt broadcast traffic. And because every client has this key, every client can also then abuse this key to spoof broadcast and multicast traffic. So basically, in a hotspot, broadcast traffic is not properly protected, and an adversary can also spoof broadcast traffic. And in fact, an adversary can even spoof unicast IP packets in a broadcast Wi-Fi frame. So we tested the following devices here, and against these devices, we can put a unicast IP packet in a broadcast Wi-Fi frame. So the summary there is we can abuse this shared key that is used to protect broadcast traffic to inject plain text, to inject unicast IP packets to any client in the network. Okay, so we now saw a lot of possible attacks. And the last thing I want to do is to give an overview of the framework that we made. So if you scan the following QR code, you will have a link to our framework on GitHub. And some of the attacks that we discussed today are available in this framework, along with some other vulnerabilities that some other people discovered. So if you want to perform some of these attacks, you can visit our GitHub page. Conclusion is that WPA3 is still affected by disconnection attacks, meaning even when using WPA3, you can disconnect the client from the network. The second thing to remember is in these special hotspot networks, you can still intercept traffic of a victim by using network-based attacks like ARP poisoning. And with that, I would like to thank you for your attention. If there are any questions, feel free to ask them.
Thank you, Mathy. Yep, I think there are a few questions. The first one is about side channel attacks. Could you describe a general methodology and the tools required on how to discover potential vulnerabilities?
Yeah, so that's a good question. I know in a lot of previous research, people discovered these side channel attacks manually. So a lot of the new side channel attacks are discovered manually. There are some research tools that allow you to automatically do this, where you can have 2 runs of a program and then see whether different instructions are executed in those 2 runs. Those are usually research tools. I haven't used them myself, but they exist. But the summary is usually people discover this manually.
All right. Did the person who asked the question, is the person here? Nope. Okay. Second question. Can compromised IoT devices which are connected to WPA3 access points perform the attacks mentioned earlier on, which is the draining of batteries, of the router who have enabled beacon protection? Is there a mitigation against such attacks?
So I think if you have beacon protection enabled, then these battery draining attacks are, to the best of my knowledge, no longer possible. Protecting against all denial of service attacks is generally hard, but at least these easy denial of service attacks that we did by spoofing the beacons, they would no longer be possible. So I would say that the message there is, yes, enable beacon protection because that prevents these attacks.
All right, thanks. One just came in, I guess. Does the group key attack apply if client-client communication is disabled?
That's a good question. I think it depends how client-to-client communication is disabled. So it depends how a vendor implements this. Sometimes if you select a switch to disable client-to-client communication, it will really prevent clients from sending data to each other, and also prohibit broadcast traffic, so you can no longer so you can no longer abuse the group key. But this depends a bit on the device. I think in general, is that if you prohibit client-to-client traffic, I can imagine in several cases, and maybe many cases, abusing the group key is probably still possible. So it's best to make sure that you disable both client-to-client traffic and you make sure that abuse of the group key is prevented. And if you want more information on this, there's also a standard called Passpoint that goes into this in a bit more detail.
All right, thank you. Is the person who asked this question here? Nope. All right. If there's nothing else... Oh no, there is one more. What about more modern Android version devices? Unicast, Packer, and Broadcast Frame. Did you examine why Pixel phone was not vulnerable, but modern Linux is?
So we didn't confirm this in detail, but I do have a hunch. My hunch is that the Android device that we tested, so the Pixel, if I recall correctly, the Pixel 4 XL, I think it's because it's using a custom Wi-Fi driver on top of the Linux kernel that is somehow blocking this. But the Linux kernel itself allows unicast packets in broadcast Wi-Fi frames. There is a kernel option to block unicast IP packets in group Wi-Fi frames, but by default it's not enabled for some reason. So yeah, I think it's because on Android, the driver, maybe of Broadcom or whatever vendor on top of the Linux kernel is somehow preventing this. That's my hunch.
All right. Thank you for the question. Is there any more? No? All right. Thanks again, Mathy.